Okay, there clearly is not enough room here on this slide to add anything new, but I just wanted to refer back to the fact that these numbers, 416, 512, 422, they were derived by comparing let's say we're at 416 at this city, and we say, what should we do next? Well, we can either fly to that city, take that flight, in which case we make it a benefit in that new city, minus the cost of getting there, or we can go to this city with the benefit minus the cost of getting there, or to this third city. And we imagine that the highest of those is coming to this city, that if you take 376 plus the benefit to be had in this city minus the cost, that was the best way to go, and that's why this arrow went this way. And all we're going to need to do now is we need to write this down as a mathematical relationship. And that mathematical relationship is called the Bellman recursive equation. And it's very simple, actually. And that's why Bellman's name has sort of disappeared. FT-ST. In other words, if I want to know what this 416, how to derive this 416, well, it will be an optimization. It could be either a min or a max, but in this case, I'm trying to find the maximum benefit. So it's a max over all possible flights that I could take. And when I take a flight, I'm going to incur an immediate consequence, which is the benefit that I'm going to have from the next city that I end up in, minus the flight or the cost of the flight. That's an immediate benefit. And I'm going to add that to the benefit from that next stage on to the end, the equivalent of the 342. Well, that will be ft plus 1. Now, ft plus 1 will be a function of st plus 1, right? But st plus 1, I can write that down, st plus 1. But this is a little frustrating because I don't know what st plus 1 is. So if I look back and I look at the transition relationship, I know what st plus 1 is. So maybe I can do this right away and erase that st plus 1 and write its equivalent, which is gt st xt. Now this looks very complicated, but it turns out to be quite simple in given problem situations. That's what we're going to do next in a given problem. So this is the Bellman relationship, and this is for all st. Now there is some additional terminology that I will introduce next time around. But before I do that, there is a problem here because we start with t, st, and also we start with t, and we'll start at the end, and then we'll go t minus 1, right? And then we'll proceed until we get to 1. So if we start with t, if we start at the last stage, well, what is the benefit of being in LA? The benefit, the 342 will include the benefit of doing business in LA minus the cost of getting there. So if that already has been incorporated in the 342, then what is the benefit of being in LA? Well, I guess you go to the beach. So what you have to, in order to start this, you need to define what is for all possible end states, and sometimes there's only one, in our case LA, what is the additional benefit? And in our case, FDST has to be defined. So I will just say okay, so for all the dynamic programming models, you need to write down the equivalent of the Bellman equation, and you also need to know, you need to write down starting, like a battery value of how do you start this process. Because once you have the last one, then you can work out the one before that, and you can work out the one before that, and you can work out right what the beginning. Now, one other thing that I should mention is that as you do these maximizations, you need to record what need to record X, T, S, T. What is the optimal decision? And this is what these were the arrows. So you need to put the arrows, like I like to think of like you're solving these problems with a bunch of arrows, signs under your arm, and as you determine the optimal decision, you put up a sign and saying, if I'm ever here ever again, this sign will tell me what to do next. Because that's what you're going to do. You're going to move from LA to PEI, doing all these calculations. Once you get to PEI, you're going to know what the immediate action is, to go to the city where it says 2612, and then you're going to look at all these signs that you put up on when you were moving from left to right. You're going to counter those signs when you go from right to left. Now, clearly, you're not going to pass when you go from right to left. You're going to do only the optimal path, and you're not going to be using many of the signs that you put up. So coming back here, these are the signs that you need to record, and at the end, this is how you can solve the problem. So the next thing what we're going to do is we're going to take an example and work through the example to show you that this is not as bad as it looks.